Okay, hi everybody. I'm going to go ahead and do a little help with the next homework section. That's 9.4. And so just real quickly, I want to go ahead and jump in. This is a test for normality. And so we're going to just do problem one again. This is what I did in class last time. There's only 3 questions here, so I don't want to ruin all your fun. So this is called the Ryan Joyner test for normality. And without going through too much trouble here, we just kind of notice we've got these hummingbird wing flaps per second or whatever they are. And so we want to determine if we can at least assume that these values are sampled from a normal population. There's 9 values here. And with 9 values, that makes 10 regions on a bell curve because each value is surrounded by 2 regions. You get one more region than you have values. So with 9 values and the total area of a bell curve is 1, we're dividing it up into 10 areas. So each area would be 1/10, which is 0.1. You just do 1 divided by the number of regions. 1 divided by 10. And so that's fine. And then you want these regions to all have equal area under the bell curve. And so they all need to have an area of 0.1. And we have to determine the z-scores that do that. And while I determine these z-scores, it'll make a graph called a normal quantile plot. And it'll match the z-scores here, which are z, with the wing flaps per second, which are the 76.8 and the 78.5 down here. Those are the wing flaps up here per second by the hummingbirds. So we want to make sure one of these samples is perfectly normal in distribution before we make the comparison. So we just slide this up until this area here is around 0.10. So I'm just going to bring it up. And this one actually works out real nicely to exactly 0.100. Okay. The next one needs to be the same as well. So I'm going to move this region, this little slider. You're not going to get exactly 0.100 on these, but you just want to get as close as you can. This one comes up to 0.1011. Okay, I'm going to make this one a little bit smaller. Try. This is actually super close to 0.100. So here, let's set that right there with a 0.0987. That's off by 13, below the 100 mark. If you go to the other side, you're off by 27. So that's way too much. So I'm going to go back to here. 0.0987 is really close to 10%. Okay, same thing here. Now all these z-scores will be the absolute value of the negative ones over here. So this one's going to be a 0.25. This one's going to be a 0.84. No, 0.52. Next one's 0.8. Oop, I messed up. 0.52. And the next one's 0.84. And the last one would be positive 1.28. Like that. All right, and then then we assess whether these points line up like a straight line. The z-scores are perfectly normal in their arrangement, and the x-scores, this would form a straight line if x's had the same distribution. It's not really a straight line, but it's pretty close. So this will do a quick, when you submit, you'll get a check on all your points to make sure they're all right. It allows a little margin for error on each of these, so small mistakes should not affect. Like for instance, if I was to screw this one up and go with a 1026 here, that's actually wrong, but I don't know if it'll let me do a resubmit down here. So that's actually a little bit wrong. It should have been 0.25, I think. And but it still counted that point as okay, so we're just going to let it go. And you get your R value here is 0.9813. That will be affected by using the wrong point here. So again, the correct value here should be 0.25 there. the R value is now 0.9811, which is a little different, but it shouldn't affect the outcome of the hypothesis test. And so with the hypothesis test, you just need this R value to be bigger than the critical value. And again, we had 9 data points here, and we have to look to see what the alpha is. So our alpha is 0.05 with 9 data points. So if you look here, with 0.05 and 9 data points, it's 0.912. I don't know if I can highlight that. So it's 0.912 here, so that's the critical value. And I'll go ahead and enter that. And so we're good to go with the critical value. And so the rule is just as simply here, down here, I believe it says, it gives the correlation coefficient, which was the 9813 on the graph up here. That's actually, wait a minute, what's going on? The R should have been 9813, which means I made a mistake somewhere. Oh, I did. That's because the, let me see if I can just go through it. This should have been 0.84 right there. And make sure everything else is right. Okay, that's good. So now it says 9813 for R. And this is agreeing it should have been 9813. That's good. Critical value 912, which is what we got up here. And so you just need your R value to be bigger than the critical value to say that normality is plausible. And so yes, our R value is bigger than the 912. So here we'll say fail to reject the null hypothesis. It's good because now we can say normality is plausible. And I'll submit, and we should get it all good to go. So that's it for this section. Super easy.